Hi everyone, the dipole moment and molecular structure. So, the dipole moment is one of the important properties used extensively to obtain the information about molecular structure. It helps in understanding the geometry of the molecule, especially the angles between the bonds and the extent to which the bond in polar molecules is polarized or ionic in character. So, here dipole moment data can be also used to decide the extent of ionic character in the chemical bond. Another important application of the dipole moment in the determination of chemical constituents is the cis or trans isomer due to presence of the double bond. So, here friends, let us consider one by one. So, here the first application of the dipole moment or use of the dipole moment, that is the percentage ionic character. So, here percentage ionic character, study of the dipole moment is useful to determine the percentage ionic character of the molecule. So, here consider the simple heteronuclear diatomic molecule, that is the HCl. Its dipole moment is 1.04 dBA, that is the observed dipole moment, and the bond length of the HCl, it is a 1.275 into 10 raised to minus 8 centimeter. So, here if the shared pair of electron was held completely by the chlorine atom, the molecule would have consisted of H plus and Cl minus ion. In that situation, HCl molecule would have 100% ionic character, but here the dipole moment in that case it will be, so mu ionic is equal to Q into L. So, all of you know that Q is the charge, it is a 4.8 into 10 raised to minus 10 ESU, and here L is the bond length, it is given here 1.275 into 10 raised to minus 8 centimeter. So, here finally it is a 6.12 into 10 raised to minus 18 ESU centimeter, that means 6.12 dBA. So, here if the pair of bonding electrons was equally shared, the electrons would be equidistant from the chlorine and hydrogen atoms, so that the dipole moment is 0. But here the dipole moment of the HCl is intermediate between these two extreme points, that is from 0 to 6.12. So, here we can find out the percentage ionic character, and to determine the percentage ionic character, the formula is mu observed divided by mu ionic multiplied by 100. So, here the mu observed is 1.04. So, here 1.04 mu ionic, it is a 6.12. So, 6.12 multiplied by 100, that is a 16.9934. That means here the ionic character of the HCl is 17%. So, with the help of the dipole moment, we can find out the percentage ionic character. This is the first use or first application of the dipole moment. Then the second one is the bond moment. If the two atoms constituting a chemical bond differ in the electronegativities, then there arises unequal sharing of electrons, and hence dipole moment may be associated with each bond, and it is referred as the bond moment. In absence of the dipole moment in molecule, for example, here H2, N2, Cl2. So, there is no dipole moment, mu is equal to 0. It indicates that the electron pair binding the atoms are situated equidistant between the constituents of the molecule. When this is not true, then such molecules they possess the dipole moment. If the two atoms constituting a chemical bond differ in electronegativity, then there arise unequal sharing of electrons, and hence the polarity of the bond arises. That is every bond has the bond moment. So, let us consider here example carbon and hydrogen. So, its bond moment is 0.4 dBA. Carbon and chlorine, here its bond moment is 1.5 dBA. Carbon and oxygen, that is the carbon monoxide, so 2.3 dBA. So, here hydrogen and oxygen, it is a 1.5 dBA. So, every bond, polar bond has the bond moment. So, with the help of the bond moment, expected dipole moment of the molecule can be calculated after depicting the probable geometry of the molecule, that is knowing the probable bond angle in the molecule for its various conformation. So, with the help of the bond moment, so here expected dipole moment of the molecule can be calculated. So this is the second application, that is the bond movement. Let us consider the next one, determination of the geometry of the molecules. So here the dipole moment data, it is also very useful to determine the geometry of the simple molecule. So here the measurement of the dipole moment provide information concerning the shape of the molecule. The following examples will clearly show that the value of this method in the determination of the structure of the molecule. So here there are two types of the compounds, inorganic compounds and organic compounds. So let us consider one by one. First of all, we will consider the inorganic compound. So here in inorganic compound there are various cases. So let us consider one by one. The first one is the monoatomic molecules. So all of you know that the zero group element, that is a helium, neon, argon, krypton, xenon, radon, they are the monoatomic gases, and here they possess the zero dipole moment. Then second one is the diatomic. So when we consider diatomic molecules, it may be polar or non-polar. So here in case of the diatomic, there are two types of the molecule, homodiatomic and the heterodiatomic. So here the homodiatomic molecule O2, H2, N2, Cl2, they have the zero dipole moment. So let us consider this case Cl2 molecule. Both the chlorines are electronegative atoms. So here, but here both the atoms or both the constituents are the chlorine, the shared electron pair is equally shared, that is why here mu is equal to 0. So there is no dipole moment in case of the homodiatomic molecule. So this indicates that electron pair binding the constituent atoms are at the same distance from the two atoms. So such molecules are quite symmetrical. So here this O2, H2, N2, Cl2, these are the symmetrical molecules, so they do not have the dipole moment. So here heterodiatomic molecules. So here the diatic molecule are polar if the bond formed between the atom is polar. So example HCl, HF, HI, this carbon monoxide. So here all of you know that when we consider the case of the HCl, chlorine is more electronegative as compared to the hydrogen. The shared electron pair is attracted to the chlorine. So the chlorine has the partial negative charge while the hydrogen has the partial positive charge. The bond is the polar bond, and here this HCl, it has the dipole moment. So here hydrogen iodide, its dipole moment is 0.38 dBA. So here the monoatomic molecules, diatomic molecules. Then let us consider the triatomic molecules. So here in case of the triatomic molecule, let us consider the example of the carbon dioxide as well as the carbon disulfide. So here in case of the carbon dioxide, both the carbon and oxygen bonds are polar. That is the bond between the carbon and oxygen, it is a polar bond, but the molecule is non-polar, that is the mu is equal to 0. So here in case of the carbon dioxide as well as in case of the carbon disulfide, mu is equal to 0. This indicates that is the carbon dioxide molecule is a linear and symmetrical. Similarly here carbon disulfide, it is also linear and symmetrical. The dipole moment of the one side, that is the dipole moment of this side, is cancelled with the dipole moment of the other side, and the net dipole moment is equal to 0. This is the case in case of the carbon dioxide, the same case in case of the carbon disulfide. So these carbon dioxide as well as the carbon disulfide both are linear and symmetrical. So here the mu is equal to 0. So the same can be true for the carbon tetrachloride as well as the stannous chloride. So here similarly, if the molecule has zero dipole moment, the molecule has center of symmetry as above. So here in case of the triatomic molecule, let us consider another example, triatomic molecule, that is H2O and sulfur dioxide. So here water and the sulfur dioxide has the dipole moment, indicate that their structure is not linear, they have the band structure as shown below. So this is the water molecule, this is the sulfur dioxide. So here the water and sulfur dioxide both have the band structure. So here these are the non-linear molecule, and here the mu is equal to, in case of the water it has a dipole moment and its value is 1.84 dBA. In case of the sulfur dioxide, its value is 1.6 dBA. So here this is the case in case of the water as well as the sulfur dioxide. Then here the next case in case of the tetraatomic molecule. So here when we consider the tetraatomic molecule of type AX3, the following arrangements are possible. There are three arrangements. So let us consider one by one. The first arrangement, the three atoms may be symmetrically arranged about the dissimilar atom all the atom being in the same plane and angle between the bond being equal to the 120 degree. So here the example is the BF3. So here this is the structure of the BF3, and here the angle is 120, here also angle is 120, here angle is 120. That means this BF3 it has the symmetrical or it has the planar structure. So here the mu is equal to 0 in case of the BF3. That is, a BF3 molecule is the non-polar molecule, it does not have the dipole moment. That is why here the mu is equal to 0 because of the symmetrical or the planar structure. This is the case number 1. Then the second case, the three similar atoms may be unsymmetrically arranged about the dissimilar atom, all the atom being uniplanar, and such a molecule have very small dipole moment. It is not equal to 0, but it has very small dipole moment. This is the case number 2. Then case number 3, the dissimilar atom will lie out of plane containing the three similar atoms, thus giving a pyramidal model to the molecule, and the best example is the ammonia. So let us consider the case of the ammonia. In the like manner, dipole moment of ammonia can be explained on the basis of a triangular bipyramidal structure in which the nitrogen is situated at the apex of the pyramid and hydrogen lie at the other three corners. So here this is the triangular bipyramidal structure of the ammonia. So here ammonia is the polar molecule, it has the dipole moment. So here the fact that ammonia, phosphine and the trihalide of the phosphorus and antimony have the definite dipole moment indicate that they belong to the case number 3, that is they are to be pyramidal model. So here ammonia. Then here let us consider the polyatomic molecule type AX4 possess the regular tetrahedron structure, have no dipole moment. So here if the molecule has the regular tetrahedral structure, such a molecule they do not have the dipole moment and mu is equal to 0. So here the example is silicon tetrachloride or titanium tetrachloride or the methane. These molecules their dipole moment mu is equal to 0. Then organic compounds. So let us consider simple organic compounds. So here when we consider the hydrocarbon that is a CH4 and they are homologous, that is a methane, ethane, propane, butane, pentane, hexane and so on, and aromatic hydrocarbon they have the 0 dipole moment, or if they have the dipole moment it is very small or it is a negligible. Then here the 6 carbon atom of benzene ring lie in one plane. The aromatic molecules such as benzene, naphthalene, diphenyl or anthracene here have planar structure, and in general all the molecule possessing center of symmetry are the nonpolar. So here the benzene, naphthalene, then anthracene they have the planar structure, they do not have the dipole moment, mu is equal to 0. So such molecules they are the nonpolar molecule when we consider the benzene ring. But here if hydrogen atom of a hydrocarbon is replaced by the another atom or radical, let us consider the case of the methane. In case of the methane, when the one hydrogen is replaced with the Cl, then here this methane it become the polar. So or when we consider the benzene ring, when the one hydrogen it is replaced with the another atom or another radical, then it become polar. So here the moment is produced which is a characteristics of the substituent in question. This moment is called as the group moment, and the moment of the substituents are to be regarded as a vector. So here let us consider one example that is a di-substituted benzene ring and angle between the substituents. So here the example is a dinitrobenzene. So here there are 3 cases of the dinitrobenzene, that is a ortho, meta and para. So this is the ortho dinitrobenzene, this is a meta dinitrobenzene, this is a para dinitrobenzene. So here in case of the ortho dinitrobenzene, the angle, that is the position inclined at the angle, it is a 60 degree, while in case of the meta and para inclined with the angle 120 degree and here the 180 degree. So here the measured dipole moment of ortho and meta para substitute benzene derivative have revealed the fact the benzene is a planar hexagon. So here in case of the multi substituted benzene ring or the disubstituted benzene ring, the dipole moment is determined with the help of the formula mu is equal to under root mu 1 square plus mu 2 square plus twice mu 1 mu 2 into cos theta. In case of the ortho compound, this theta value is 60 degree. In case of the meta, it is a 120, while in case of the para, it is a 180. And mu 1 and mu 2, these are the two dipole moment of the two substituent in the benzene ring. So here, in case of the ortho dinitrobenzene, mu is greater than 0, it is not equal to 0, it is greater than 0, while in case of the meta dinitrobenzene, mu is also greater than 0, but here in case of the para dinitrobenzene, mu is equal to 0 because it has the symmetrical structure, while this ortho and meta dinitrobenzene, they have the asymmetrical structure, so their dipole moment is greater than 0. And here friends, when the in case of the disubstituted benzene ring, when the both the substituents are same, then this formula can be reduced to, in case of the ortho dinitrobenzene, the formula is reduced to mu is equal to mu 1 under root 3. Directly we can substitute the value of the mu 1, you will get the value of the mu. Then in case of the meta dinitrobenzene, this mu is equal to mu 1, and in case of the ortho dinitrobenzene, not ortho, that is the para dinitrobenzene, this is the mu is equal to 0. So here disubstituted benzene ring and angle between the substituent. So here mu 1 and mu 2 are the dipole moment of the two group substituted in the benzene ring. Theta is the angle at the direction the moment are inclined. The dipole moment, again it is the same formula, mu is equal to under root mu 1 square plus mu 2 square plus twice mu 1 mu 2 cos theta, or mu 2 square is equal to mu 1 square plus mu 2 square plus twice mu 1 mu 2 cos theta. Just by substituting the value of the mu 1 mu 2 as well as the theta, here we can find out the dipole moment of the disubstituted benzene ring. So here the last application of the dipole moment, cis and trans structure in the organic compound. By dipole moment measurement, a distinction between the cis and trans isomer due to presence of the double bond can be immediately made. Due to symmetry, trans compounds have very low or zero dipole moment, while the cis compound have appreciable dipole moment. That means here the trans compounds are the non-polar, while the cis compounds are the polar molecule. So here cis form will be the polar and the trans will be the non-polar. This has been confirmed by experiment in case of the fumaric and malic acid. So here these are the structure of the malic acid as well as this is the structure of the fumaric acid. So malic acid is the polar, and while the fumaric acid is the non-polar. So here with the help of the dipole moment, we can distinguish between the cis and trans structure in case of the organic compound. So these are the various applications of the dipole moment. So thank you friends.